Good morning. My name is Sakshi. This is Organic Chemistry, Semester 4. The chapter name is Nitro Compound. Introduction. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbon by the replacement of one or more hydrogen atom by nitro groups. Nitroarenes, that is nitro compounds in which another group is directly attached to benzene ring, can be prepared rather easily and have been used as synthetic reagent since long. But nowadays even nitroalkanes are being prepared and used on a large scale. Structure and nitro compound. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or a dative bond between nitrogen and other oxygen. But actually nitro group is established by resonance and is a hybrid of two equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that the bond length of each nitrogen oxygen bond is 121 picometer or 1.21 angstrom, which is intermediate between NO single bond length 136 picometer or 1.36 angstrom and NO double bond length 115 picometer or 1.15 angstrom. In case of nitroarenes, resonance of two nitro group with the ring can also take place, giving rise to additional contributing structures for the molecule. It will be interesting to note that the nitro group is isoelectronic with carboxylate ion. Nomenclature of nitro compounds. The nitro compounds are named by writing the word nitro before the name of parent compound. The number of nitro groups and their positions are also suitably indicated as illustrated below. CH3NO2 nitromethane, CH3CH2 NO2 nitroethane, CH3CHNO2 CH3 2 nitropropane, CH3CHNO2 CH3CH3 2 nitro 3 methylbutane, nitrobenzene, orthonitrotoluene, metadinitrobenzene, paranitrophenol. Classification of nitroalkanes. Nitroalkanes are termed as primary, secondary, tertiary, according as a nitro group is attached to a primary, secondary, or tertiary carbon atom. That is, RCH2NO2 is primary nitroalkane, RCRHNO2 secondary nitroalkane, three alkyl groups attached on a carbon and NO2 tertiary nitroalkane. CH3CH2NO2 nitroethane primary, CH3CH3NO2 2 nitropropane secondary, CH3CH3CH3C NO2 2 methyl 2 nitropropane tertiary. Preparation of nitro compounds. Preparation of nitroalkanes. Nitroalkanes are usually prepared by following method. First is vapor phase nitration of alkanes. The reaction involves the substitution of hydrogen atom of the alkane by a nitro group. It is carried out in vapor phase by heating the alkanes with nitric acid at about 700 Kelvin. RH plus HNO3 at the temperature of 700 Kelvin gives RNO2 plus H2O. Limitation of this process: during nitration of higher alkanes, all possible isomeric nitro products are formed. Moreover, rupture of carbon-carbon bond also take place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane results in the formation of a mixture of four nitro compounds, which gives CH3CH2CH3 in the presence of HNO3 at 673 Kelvin temperature. It gives CH3CH2CH2NO2 1 nitropropane plus CH3CHNO2CH3 2 nitropropane, CH3CH2NO2 nitroethane plus CH3NO2 nitromethane. Due to the formation of complex mixture of product, this method is not used for laboratory preparation of nitroalkanes. However, the method is widely used for commercial preparation of nitroalkanes since they are used as industrial solvent only. Mechanism. The reaction is believed to involve the formation of free radical, but the mechanism is not well established. Second is action of silver nitrate on aryl halide. This is method This is method generally employed for laboratory preparation of nitroalkenes. When heated with silver nitrate, alkyl halide undergo nucleophilic substitution to form nitroalkane along with small quantities of alkyl nitrites. This is because NO2 negative is an ambidendant ligand. Rx alkyl halide plus AgNO2 gives RNO2 nitroalkane major product plus RONO alkyl nitrite minor group plus AgBr. However, mixture of alkyl nitrates and nitroalkanes can be separated by fractional distillation. Oxidation of amines. When an amine is in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Tertiary nitroalkane plus 3O in the presence of K-amino4 gives tertiary nitroalkane plus water molecule. Preparation of nitroarenes. Nitroarenes are almost variable prepared by direct nitration of arenes. The nitrating agent generally used are concentrated or fuming nitric acid. Mixing of concentrated or fuming nitric acid with concentrated sulfuric acid. Sometimes fuming sulfuric acid is also used. This mixture is the most commonly used as nitrating agent. Mixing of concentrated nitric acid with acetic anhydride or boron trifluoride. Acetyl nitrite CH3COONO2 obtained by mixing nitrogen pentoxide and acetic anhydride. Nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent to be used for the nitration of a given compound depend upon the following two factors: nature of the compound to be nitrated. Second is number of nitro compounds to be introduced. In the nitration of aromatic compounds containing electron releasing or activating groups such as NH2, OH and CH3, the reaction takes place readily at room temperature by employing concentrated HNO3. In some cases, even diluted HNO3 can be used. For example, phenol in the presence of diluted HNO3 gives ortho and para-nitrophenols. For nitrating compound containing electron attacking or deactivating groups such as COOH, or when it is desired to introduce more than one nitro compound, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. It may be remembered that the nitro group itself is also a deactivating group. Nitrobenzene and meta-nitrobenzene, for instance, can be obtained from benzene under the conditions shown below. Meta-dinitrobenzene is formed from when benzene is reacted with concentrated HNO3 plus concentrated H2SO4 at the temperature 373 Kelvin. When benzene is reacted with concentrated HNO3 plus concentrated H2SO4 at 328 Kelvin, it gives nitrobenzene. Mechanism of nitration. The nitration of aromatic compound, like other aromatic compound reaction, is electrophilic in nature and involves a nitrosonium ion NO2 positive as attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene with nitric acid and sulfuric acid mixture. First is generation of electrophile. HONO2 plus 2H2SO4 gives NO2 positive nitronium ion plus H3O positive plus 2HSO4 negative. Second is formation of carbocation ion. NO2 positive plus benzene gives the intermediate proton transfer from the carbocation to yield the final product. Intermediate plus HSO4 negative gives nitrobenzene plus H2SO4. Evidence in favor of above mechanism. It has been shown that the aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as electrophilic reagent, is generated in a preliminary step and brings about further reaction in two steps. The first step is a slow rate determining step involving the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. C6H6 plus NO2 positive gives C6H6 positive H and NO2. C6H5 positive H NO2 plus HSO4 negative gives C6H5 NO2 plus H2SO4. This mechanism have been fully supported by isotope tracer technique as explained below. If an aromatic compound labeled with deuterium, the heavier isotope of hydrogen having mass of 2 AMU, is subjected to nitration, it is found that the rate of substitution of deuterium is the same as that of ordinary hydrogen or protium. In other words, no isotope effect is observed. Since a carbon deuterium bond is broken more slowly than a carbon protium bond, the absence of isotope effect in aromatic nitration can be justified only if the rate determining step of a reaction does not involve any cleavage of carbon hydrogen bond. This means the final step involving reaction, the abstraction of proton through the cleavage of carbon hydrogen bond, cannot be the rate determining step. Therefore, the step leading to the formation of carbocation must be the rate determining step, as it do not involve any cleavage of carbon hydrogen bond one formed, and carbocation loses the proton relatively fast to form the final product. The absence of isotope effect also rules out the possibility of a single step mechanism of nitration. This is because single step substitution cannot take place without the cleavage of carbon hydrogen bond, such as it must exhibit isotope effect, but this is not so in actual practices. Hence, aromatic nitration is a stepwise process in which the formation of carbocation is the rate determining step. Comparison of nitration of arenes and nitration of alkanes. It may be noted that the nitration of arenes take place at relatively low temperature, whereas nitration of alkanes requires a very high temperature. This may be due to the fact that the nitration of arenes involves the initial formation of an electrophilic reagent, while the nitration of alkane is supposed to involve the initial formation of the free radical. The formation of free radical takes place through homolysis and requires stronger oxidation than the formation of electrophile, which take place through heterolysis. As such, nitration of arene take place more easily than nitration of alkanes. Nitroarenes cannot be prepared by action of silver nitrate on aryl halide because of the very low reactivity of aryl halide towards nucleophilic reagent. Physical properties of nitro compounds. First is physical state. Nitroalkanes are colorless, oily liquids when pure. They have pleasant smell and are sparingly insoluble in water, with the exception of a few compounds including nitrobenzene, which are yellow oily liquids. All other aromatic nitro compounds are yellow crystalline solids. Nitrobenzene has an odor of bitter almond and is known as oil of nirbane. Solubility and density. All the nitro compounds are heavier than water. Nitroalkanes are sparingly soluble in water, while aromatic nitro compounds are insoluble in it. They are, however, readily soluble in organic solvents such as alcohol and ether. Stability. When heated strongly, polynitro compound decomposes with explosive violence. Fourth, boiling point. Due to presence of highly polar nitro compounds in their molecule, nitro compounds have strong dipole-dipole interaction. Mu is equals to 3 to 4 T. Consequently, they possess high boiling point, much higher than the hydrocarbon of comparable molecular masses. Moreover, most of the nitro compounds are volatile in steam. The melting and boiling point of nitro compounds gradually increases with the number of nitro groups as illustrated ahead. Chemical reaction of nitroalkanes. The important chemical reaction of nitroalkanes are as follows. First is acidic nature. Tautomerism. Nitroalkanes containing alpha hydrogen atoms, that is primary and secondary nitroalkanes only, exhibit acidic behavior and form salt in the presence of strong alkalis. For example, RCH2NO2 plus NaOH gives RCHNO2 negative, Na positive and H2O. The acidity can be attributed to the fact that first, nitro group has a strong tendency within withdrawing inductive effect, that is minus I effect. Second is anion formed after the removal of proton from the nitroalkane get resonance stabilized due to the ability of the nitro group to accommodate negative charge. It is interesting to note that the salt formed by nitroalkane is acidified at low temperature. The oily drops of nitroalkanes do not separate immediately, but we get another form of nitroalkane known as acid-nitro form, which slowly changes into the nitro compounds. This is due to the fact that the primary and secondary nitroalkane exhibit tautomerism. The tautomeric form being nitro form and acid form. The tautomeric equilibrium between the two forms lies almost completely towards the nitro form because it is stabilized by the resonance of nitro group. Acid nitro form is relatively stronger than the nitro form. An important feature of acid nitro form is that it can act both as electrophile and nucleophile. Unlike primary and secondary nitroalkanes, tertiary nitroalkanes and nitroarenes do not have any alpha hydrogen atom. As such, they exhibit neither acidic character nor tautomerism. Reduction of nitroalkanes. Reduction of nitroalkanes is one of the most important reaction. The reduction of nitro group take place as stages. RNO2 gives RNO, RNHOH, RNH2 primary amine. The product actually obtained depend upon the nature of reducing agent and the pH of the reaction medium. Thus, nitroalkanes can form different product on reduction as given below. First, reduction in acidic group. When reduced in an acidic solution, nitroalkanes form primary amines. RNO2 plus 6H FeHCl gives RNH2 plus 2H2O. Catalytic reduction or reduction with LiAlH4. Reduction with LiAlH4 or H2 in the presence of nickel platinum catalyst also yield the same product. RNO2 in the presence of LiAlH4 or H2 platinum gives RNH2 plus H2O. Third is reduction in neutral medium. If the reduction is carried out in neutral solution, a hydroxyl amine derivative is obtained. RNO2 plus 4H in the presence of ZnNH4Cl gives RNHOH, alkyl hydroxyl amine plus H2O. The hydroxyl amines are readily oxidized to corresponding nitroso compounds on warming with Tollens reagent, which get reduced to metallic silver. This reaction is used as a test for nitro compounds under the name Baker-Millikan test. Hydrolysis. When boiled with concentrated HCl and H2SO4, primary nitroalkane undergo hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine. For example, RCH2NO2 plus H2O plus HCl gives RCOOH plus NH2OH HCl. CH3CH2NO2 plus H2O plus HCl in the presence of heat gives CH3COOH plus NH2OH dot HCl. Secondary nitroalkanes are hydrolyzed to ketones and nitrous oxide by boiling with concentrated HCl. 2R2CHNO2 in the boiling HCl gives 2RCOO double bond OR plus NO2 plus H2O. Tertiary nitroalkanes are not hydrolyzed by acid. Next is Neff reaction. When sodium salt of primary and secondary nitroalkanes are hydrolyzed by boiling with dilute sulfuric acid, aldehydes and ketone respectively are obtained. The reaction proceeds through the acid-nitro form of nitroalkanes. When sodium salt of primary nitroalkane react with 2 moles of H2SO4, it gives aldehyde plus 2 moles of NaHSO4 plus N2O plus H2O. Sodium salt of secondary nitroalkane when react with 2 moles of H2SO4, it gives ketone plus N2O plus H2O. In this reaction, the acid-nitro forms act as an electrophile. Fifth is action with nitrous acid. Primary, secondary, tertiary nitroalkane exhibit different behavior towards nitrous acid. First is primary nitroalkanes react with nitrous acid to form nitrolic acid, which dissolve in NaOH to produce a red solution. Nitroalkane plus HONO gives nitrolic acid plus H2O. Secondary nitroalkane react with nitrous acid to form pseudo-nitrols, which have blue color but do not dissolve in NaOH. R2CHNO2 plus HONO, it gives pseudo-nitrol plus H2O. Tertiary nitroalkyls and nitroanate do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction can be used for distinguishing between primary, secondary and tertiary nitro compounds. Sixth is halogenation. When treated with halogenation, chlorine or bromine in slightly alkaline solution, primary and secondary nitroalkanes undergo halogenation at alpha position. Nitroethane react with Cl2 NaOH, it gives CH3CHCl plus NO2, It further reacts with Cl2NaOH. It gives CH3CCl2NO2 1,1 dichloronitroethane and CH3CH3NO2. In the presence of Br2NaOH, it gives 2-bromo 2-nitropropane. Nitromethane on chlorination in alkaline medium give trichloronitromethane CCl3NO2, also known as chloropicrin. Tertiary nitroalkane do not undergo halogenation because they do not have alpha hydrogen. Seventh is condensation with aldehydes. Due to presence of active alpha hydrogen in them, primary and secondary nitroalkanes undergo aldol type condensation with aldehyde in the presence of the base to form nitrile alcohols, that is CH3CH double bond O acetaldehyde plus nitrobenzene gives 3-nitro-2-butanol. Mannich reaction. This is a condensation reaction which involves formaldehyde, ammonia, or a primary or secondary amine, generally taken as hydrochlorine, and a compound having at least one active hydrogen, such as primary and secondary nitroalkanes. For example, secondary nitroalkane, in the presence of formaldehyde plus NH4Cl, it gives nitroamine hydrochloride plus H2O. The reaction can be used for preparing nitroamines, diamines, etc. Chemical reaction of nitroarenes. Nitroarenes are chemically rather inert compound. The nitro group is firmly attached to the nucleus and cannot be replaced by other atoms or group under ordinary condition. Their important reactions are as follows. Acidic nature. Unlike primary and secondary nitroalkanes, nitroarenes do not have any alpha hydrogen atoms. As such, they do not exhibit acidic character or tautomerism. However, nitro compounds having two or more nitro groups attached to benzene ring are somewhat acidic in nature due to the strong electron withdrawing effect of nitro group on the benzene ring. Second is reduction. The most significant reaction of nitro compound in their reduction under different conditions to give different products. As already stated, the reaction take place in stages and the nature of the final product depends mainly on the pH of the reaction mixture. We will illustrate the reduction of nitroarenes under different conditions with the help of nitrobenzene. Reduction in acidic medium. On reduction in acidic medium with an active metal and acid such as zinc and HCl or tin and HCl, nitrobenzene yields aniline. Nitrobenzene, in the presence of ZnHCl or SnHCl, it gives aniline plus 2H2O. Mechanism. The reaction proposed for the reaction involves a number of steps in which addition of electron and proton take place, and nitrobenzene free radical ion and nitrosobenzene free radical anion are formed as intermediate. Catalytic reduction. The reduction of nitrobenzene with H2 in the presence of Ni or PT catalyst also leads to the formation of aniline. Reduction in neutral medium. When reduced in neutral medium, example with zinc dust and ammonium chloride solution, the reaction stop at the hydroxyl amine stage. Phenol react with Zn aqueous NH4Cl, it gives NHOH phenol plus H2. Reduction in alkaline. On reduction in alkaline medium, nitrobenzene yield different product depending upon the nature of reducing agent employed. Nitrobenzene, when react with Na3ASO3 in the presence of NaOH, it gives azoxybenzene. When nitrobenzene react with ZnNaOH in CH3OH, it gives azobenzene. When nitrobenzene react with ZnNaOH, it gives hydroazobenzene. These products are actually formed by further reaction between the primary reduction product, that is nitrosobenzene, and phenyl hydroxyl amine. There is sufficient evidence to show the azobenzene is formed through the intermediate formation of azoxybenzene and its further reduction. Hydroazobenzene is similarly formed by further reduction of azobenzene. Fourth is reduction with LiAlH4. Reduction of nitrobenzene with LiAlH4 also yield azobenzene. 2 moles of nitrobenzene in the presence of LiAlH4, it gives azobenzene. Electrolytic reduction. When reduced electrochemically in weak acidic medium, nitrobenzene give aniline, but on electrolytic reduction in strongly acidic medium solution, nitrobenzene yield para-aminophenol due to rearrangement of phenyl hydroxylamine first form. Nitrobenzene in the electrolytic reduction and weakly acidic medium, it gives aniline. Next is selective reduction. In case of compound containing more than one nitro group, it is possible to carry out selective reduction of some group by employing a mild reducing agent such as ammonium hydrosulfide NH4SH or sodium polysulfide Na2SX for example. Meta-dinitrobenzene plus 3NH4SH gives meta-nitroaniline 3S plus 2H2O plus 3NH3. This reduction is known as Zenin reduction. Electrophilic reduction. Nitro group, being an electron withdrawing group, has a strong deactivating effect on electrophilic substitution reaction of benzene nucleus. However, under strong condition, nitro group compound may undergo electrophilic substitution in meta position with respect to the nitro group. For example, metachloronitrobenzene is formed from when nitrobenzene react with Cl2FeCl3. When nitrobenzene react with fuming HNO3 and concentrated H2SO4, it gives metadinitrobenzene. When nitrobenzene react with fuming H2SO4, it gives meta-nitrobenzene sulfonic acid. It may be noted that nitrobenzene does not undergo Friedel-Crafts reaction. Next is nucleophilic reaction. The nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature, but this very electron withdrawing influence of the nitro group makes the benzene nucleus liable to attack by nucleophilic reagent. Thus, unlike benzene, nitrobenzene on heating with sodium hydroxide gives small amount of ortho and para nitrophenol. When nitrobenzene react with OH negative, it gives ortho and para nitrophenol. Next is replacement of nitro group. In case of polynitro compound, one of the nitro compound itself can be replaced by nucleophilic group. When para-dinitrobenzene react with 2 moles of NH3, it gives para-nitroaniline N2 plus 2H2O. When para-nitrobenzene react with KOH, it gives para-nitrophenol plus KNO2. When para-dinitrobenzene react with C2H5ONa, it gives para-nitrophenol plus NaNO2.